Imagine we have a spherical conductor with a cavity inside of it. And in that cavity, we've kept a positive charge. Let's say imagine it's floating in air over there, okay? And it's not at the center right now. The question you want to try and answer is this. See, this positive charge is going to start producing an electric field. And that electric field is going to start sucking the electrons from this metal. Remember, metals have free electrons. They can move under the influence of electric field. So as a result of that, electrons will get sucked in. And so there will be some negative charge getting induced over here. As a result of that, there will be some positive charge getting induced on the outer surface. And as a result of that, our electric field is going to get modified. So the question is, once all the electrons have stopped moving, once we have reached electrostatic condition, we have to answer 3 questions. What will be the total charge on the inner surface and how the distribution would be? What would be the charge on the outer surface and how the distribution would be? And what would the new electric field lines roughly, the sketch of that, how would that look like? So these are the 3 questions we're going to try and answer. So how do we do this? Where do we even begin? This looks like a very complicated, challenging puzzle. Well, what I like to do, let me first dim the electric field lines a little bit. All right. So what I like to do is go back to one of the basic things we've seen about conductors and electrostatics. We've seen that in electrostatic conditions, conductors should always have 0 electric field inside of them. Why? Because if there are any electric fields over here, they will start pushing on the electrons and the electrons will start moving. That means we are not in electrostatic condition because electrons are moving. So whenever we are in electrostatic condition, automatically it means that there are no electrons moving. Automatically it means that the electric field must be 0. And if you need a more refresher on, on this concept, we've talked about this in great detail in a previous video on electrostatic shielding. So feel free to go back and check that out. But anyways, let's come back to our question. We know because of this electric field generated by the positive charge, it's going to start, sucking in negative charges. So there'll be some negative charges over here. And because our conductor is neutral, if there are some negative charges which are induced over here, because of that, some equal number of positive charges should get induced on the outer surface. So there should be some positive charges induced on the outer surface. And our goal is to figure out how much these are. Okay? Because we are given that this inner charge is plus Q. So let's start with the induced inner charges, the purple charges, negative charges. How much would that be? Would it be equal to negative Q? Would it be more than negative Q? Would it be less than negative Q? Or do you think it's possible? Do you think there is not enough information? We'll not be able to calculate that. How do we do this? How do we figure out how much these negative charges could be? Well, at first it looks like, how do I know? Like, how would I know in the electrostatic situation exactly how much of the negative charges would come? Maybe it depends upon the position of this charge. Maybe it depends on the strength of this charge. I don't know for sure. So how can I calculate that? Well, we can use this to our advantage. We know that the electric field has to be 0. So the negative charges induced must be in such a way that they should kill the electric field over here. But how? How do I figure out exactly how much? What is the connection between charges and electric field? Ooh, Gauss's law. Gauss's law is the one that connects charges and electric field. So why don't you pause the video and see if you can somehow use Gauss's law to figure out exactly how much negative charge should be induced inside. So why don't you pause the video and think about that? So what I would like to do is I'm going to choose a Gaussian surface and make sure that Gaussian surface, the entire surface, choose a sphere, but the entire surface lies within the bulk of the conductor. So imagine this is my spherical Gaussian surface. Now, because I know that under electrostatic conditions, electric field everywhere over here is 0, therefore I know that the total flux through that surface must be 0. So net electric flux must be 0. Which means that the total enclosed charge must be 0. And from that, I think I now understand how much this negative charge should be. If the total enclosed charge should be 0 and I already have plus Q, that means that the total negative charge must be negative Q. So this should be negative Q. Only then the total enclosed charge becomes 0. And what's amazing is that it doesn't matter where I position this little Q. It doesn't matter where I move it. The total induced must be negative Q. And therefore, the total induced on the outer surface should be plus Q. It has to be, because we know that the conductor is neutral. So if there is negative Q induced on the inner surface, plus Q must get induced on the outer surface. So the charge on the outer surface is plus Q, the charge on the inner surface is negative Q. And so what's interesting is whatever charge we introduce inside, automatically that charge gets manifested on the outside. Wonderful, isn't it? That's an amazing thing about a conductor. But we're not done yet. We also need to look at the charge distribution and what the electric field looks like, what the new electric field is going to look like. So let me bring back the original electric field. Here it is. So this would have been the electric field at the beginning before all of these charges got induced. The question is, what would this new electric field look like? Let's do this in steps. Let's first look at the electric field in this region. What's gonna happen to that? We know that electric field has to be zero in understanding electrostatic conditions. So we can go ahead and rub that. So let me do this. This electric field is gonna disappear. All right, so we got one part solved. The next question I want to try and answer is, how would the new electric field inside look like? Would it look exactly this way? Would it just look like this, or do you think it's going to change? Again, can you pause the video and think a little bit about this? All right, we know that because the entire conductor has zero electric field, it's an equipotential surface. Again, something that we have talked about in previous videos. But because our conductor is an equipotential surface, that means the electric field over here must always be perpendicular to the surface. And you can see that these electric field lines are not. Over here, they're not perpendicular, which means these electric field lines are going to bend in such a way that they try to be perpendicular wherever they meet the surface. So the way it's going to look like, again, it's a rough figure. The electric field lines are going to bend somewhat like this, from positive to negative, but they'll also always ensure that the angle between the field lines and the inner surface is going to be 90 degrees. All right, I have another question for you. How do you think would the charges get how would the charge distribution look like? Do you think it's going to be a uniform charge distribution over here, or do you think there's going to be, some part is going to have more concentration while some part is going to have less concentration? Again, can you pause the video and think about how the charge distribution would be on the inner surface, this negative Q? All right. So because the charge is closer to this surface, and you can see the electric field lines over here are stronger, and they're close to each other, and the electric field over here is far away, and which means it's weaker, we can immediately guess that there should be more charges over here, and there should be less. So you would have stronger charge distribution. I know it's a little hard to see, but there should be more charges on this side, and there would be less charges on this side. So charges will get more concentrated over here. Charges will be less concentrated over here. All right, final question. How would the outer charge distribution look like? Would it be uniform because it's a sphere? Or do you think it's gonna be, there'll be more positive charges over here because there is more negative charge over here, and there will be less positive charge over here because there is less negative charge over here? So final time, can you pause and think a little bit about how would that be? All right. Now, when I first thought about this, I thought, yeah, because there's a lot of negative on this side, there would be a lot of positive over here, lot of positive charge over here, and there should be less positive charge over here, right? But think about this. There is no electric field in between. The outer charges are sort of disconnected from what's going on inside. And that's the key, which means that the outer charge distribution is absolutely independent of how the inner charge distribution is happening. The two are literally disconnected. Therefore, the outer charge distribution does not depend upon the inner charges. It only depends upon the geometry. And because it's a sphere, we've already seen before, because of the symmetry, the outer charge distribution has to be uniform. And as a result, this electric field is also going to change slightly. Remember, this electric field now appears to be coming from this charge, but because we have a symmetric uniform charge distribution, the electric field is going to be radial. So it's going to appear to be coming from the center. And so the new electric field, outer electric field, is going to be radial. What I absolutely love about this problem is it's really challenging, but to answer that, we just needed this, the core of this is going back to the basics that in electrostatic condition, electric field inside a conductor must be 0.